Welcome friends to today's session of live lectures. For this session we have with us in our studio Dr. Vandana. Dr. Vandana is Assistant Professor in Delhi University's Dayal Singh College under Department of Chemistry. Friends, today's topic of discussion is a series of carbohydrates which fall under the topic of natural products and spectroscopy. This is the part 1 of the series. Let's welcome Dr. Vandana. We welcome you, Dr. Vandana.
Thank you so much, ma'am. Hello viewers. In this series of natural product and spectroscopy, we have delivered many lectures about spectroscopy. Hope you understood that these lectures. Now we are starting a new series, that is carbohydrates. You are very much aware of the term carbohydrates because whatever you are eating containing carbohydrate, the clothes you wearing is carbohydrate, the houses are made up of carbohydrates. So we have heard carbohydrates many times. Let us explore in details what are actually carbohydrate structure wise and what are their properties. So this is the part 1. What is the classification of carbohydrate and what are carbohydrates? We can say this is the hydrates of carbon. As you can see, it was the initial definition of carbohydrate because we can see this formula CxH2OY. Simple carbohydrates are also known as sugars or saccharides. This is a Latin word saccharum as well as Greek word saccharon, and the ending of the name of the most sugars is OSE, O-S-E. We have sucrose for table sugar, this is glucose for principal sugar in blood, fructose a sugar in fruits and honey, and maltose for malt sugar. You have heard these kind of sugars. Carbohydrates are usually defined as polyhydroxyaldehydes and ketone, or the compounds which yields these compounds on hydrolysis. Carbohydrates generally contain ketonic groups and hydroxyl groups. They are also called as hemiacetals or acetals. What are these terms? How they form? We will discuss in coming slides. Carbohydrates that undergo hydrolysis to produce only 2 molecules of monosaccharide are called disaccharides. For example, maltose and sucrose. Maltose, when hydrolysis undergo to give 2 moles of monosaccharide, one is glucose, and sucrose undergo hydrolysis to yield 1 mole of glucose and 1 mole of monosaccharide fructose. Those producing 3 molecules of monosaccharides are called trisaccharides. Carbohydrate that hydrolyze to yield 2 to 10 units of monosaccharides are also known as oligosaccharides. Carbohydrate that yield a large number of molecules of monosaccharide, let us say more than 10, these are known as polysaccharides. So starch and cellulose are the examples of polysaccharides. Both are glucose polymers, means both on hydrolysis will give the monosaccharide, that is glucose. You can see in the figure, this is a molecule of maltose. It is a disaccharide which on acidic hydrolysis is giving 2 moles of glucose, right? So it is a monosaccharide. 1 mole of sucrose will give 1 mole of glucose and 1 mole of fructose. 1 mole of starch or 1 mole of cellulose, both are polysaccharide as I told you, both are polymers. They will give you many moles of glucose monosaccharide. So you can see that on hydrolysis this will again give you carbohydrates. Carbohydrates are most abundant organic constituent of plants. They not only serve as an important source of chemical energy for living organisms, these are sugars and starch, but also in plants and in some animals they serve as important constituent of supporting tissues. And this is the primary function of cellulose found in wood, cotton and flax. Carbohydrate is also useful in our daily lives. How? The paper on which this book is printed is largely cellulose. Cotton of our clothes, wood of our houses, as I told you. The flour from which we make bread is mainly starch, and the starch is also a major constituent of many other foodstuffs such as potatoes, rice, beans, corn, peas, etc. Carbohydrates are central to metabolism and they are important for cell recognition. Photosynthesis and carbohydrate metabolism. Carbohydrate are synthesized in green plants. You know what is the process? This is photosynthesis, a process that uses solar energy, or we can say sun energy, to reduce or fix carbon dioxide. Photosynthesis in algae and higher plants occurs in cell organelles called chloroplast. The overall reaction, you might be aware of this. You can see this is the number of carbohydrate, carbon dioxide, water molecules, solar energy trap in the chloroplast, and you will get this carbohydrate. Carbohydrate act as a major chemical respiratory for solar energy. Their energy is released when animal or plants metabolize carbohydrate to carbon dioxide and water. You can see this kind of reaction can happen. A monosaccharide containing 3 carbon atom is called a triose. One containing 4 carbon atom is called tetrose, and one containing 5 carbon atoms is a pentose, and 6 carbon containing will be known as hexose. A monosaccharide containing an aldehyde group is called an aldose. So, one containing one keto group is called ketose. These two classifications are frequently combined. For example, if we are saying about C4-aldose, it is known as aldotetrose, right? And for C5 ketose, it is known as ketopentose. So, this is how we can say the particular carbohydrate is. And you can see the structure. This is an aldose, because you can see at the top or at the first carbon atom it is aldehyde group. This is ketose. This is aldotetrose, because you can count the carbon number 1, 2, 3, 4, and this is ketopentose 1, 2, 3, 4, 5. So, this is ketopentose. Now, what is the D and L designation of monosaccharides? Capital D must take care of the nomenclature, capital D and capital R, L. The simplest monosaccharides are the compound glyceraldehyde and dihydroxyacetone, and you can see the structure of both of these. This is glyceraldehyde, aldotriose, because 3 carbon atoms are there. This is ketotriose, dihydroxyacetone. Of these two compounds, only glyceraldehyde contains a stereocenter. You know what is a stereocenter? When a carbon atom has 4 different atoms or group, may be known as stereocenter or chiral carbon atom. So, if you see this carbon atom, it is chiral. It is not chiral at all. I want to repeat again, a carbon atom which 4 valencies are satisfied with 4 different atoms or group is known as chiral atom, asymmetric atom, or we can say this is a stereocenter. This is only stereocenter in this molecule, because other carbons are having the same kind of atoms or groups. Like here you can see the this oxygen is bonded to this carbon with double bond, so it cannot be a stereocenter. Again here this carbon is attached to 2 hydrogen atoms, so it is not at all a stereocenter. Only this one is the stereocenter, and this molecule also is not containing any stereocenter if you see all the carbon atoms carefully. Glyceraldehyde exists therefore in 2 enantiomeric forms. If a compound is having chiral center, or we can say stereocenter, the 2 possibilities for enantiomers are there, and they are absolute configurations. We can say you can see this is plus glyceraldehyde or minus glyceraldehyde. If you remember, while talking about stereochemistry, this plus shows D, dextrorotatory, or this minus shows in advanced nomenclature S nomenclature, that is this one is S, D, and we can say capital R or capital S, or we can say small d or small l. According to Can-Ingold-Prelog convention, glyceraldehyde plus glyceraldehyde should be designated as R plus glyceraldehyde. Whether the if we see the chirality rule, first of all we need to apply the priority rule. We have to see the all attached 4 atoms to a carbon in a priority order. Then we have to see the chiral rule also. If it is comes out R, then we can designate it as R glyceraldehyde, and if it is comes out S, we can designate it like this S. or you can also see it can be also designated as plus, and here you can see minus. Early in the 20th century, before the absolute configuration, we are talking about R or S or small d, small l. Small d means dextrorotatory, small l means levorotatory. So these are different nomenclature. Small d and small l are the absolute configuration for a stereocenter, while capital D and capital L are the relative configuration. I will discuss in detail these terms. Earlier in the 20th century, before the absolute configuration of any organic compound were known, another system of stereochemical designation were introduced, and according to this system, first suggested by M.A. Rozanoff of New York University in 1906, glyceraldehyde, this plus glyceraldehyde is designated as D plus, and this minus glyceraldehyde is designated as capital L minus glyceraldehyde. How? These two compounds moreover serves as configurational standard for all monosaccharides. So we can relate other monosaccharide with these D, capital D glyceraldehyde and capital L glyceraldehyde. What is that? If you can see these two figures, it is a aldopentose and it is in capital L ketohexose. So if you see, there are how many carbon atoms? 1, 2, 3, 4, 5, 6. So how can we define capital D and capital L for monosaccharide in the last asymmetric carbon atom? If you see, this is the last asymmetric carbon atom because this is symmetric, because two hydrogen atoms are attached to the same carbon atom. So we have to see the asymmetric carbon atom of a compound, last asymmetric carbon atom, and in this this molecule, if hydroxyl group lies on the left hand side, it will be designated as capital L, and if it is lies on last asymmetric carbon atom of a monosaccharide on the right hand side, it will be designated as capital D. So hope you understood, these are the relative configurations. You should clear that capital D, capital L, small d, small l are different configurations. Capital D and capital L are the relative configuration. The full form of D is DE, that is DE, and L for capital L, it is LAL. For small d and small l, these are, small d means full form of small d is dextro and full form of small l is levo. These are absolute configuration. Structure formulas for monosaccharides. The great carbohydrate chemist Emil Fischer was able to establish the stereochemical configuration of the aldohexose D-glucose, the most abundant monosaccharide. D-glucose is the most abundant, you must notice this. In IUPAC nomenclature with the Ken-Ingold pre-log system of stereochemical designations, the open chain form of D-glucose can be written like this. This is 2R, 3S, 4R, 5R, 2, 3, 4, 5, 6 pentahydroxyhexanal. How it is? You can see here. How many carbon atoms? 1, 2, 3, 4, 5 and 6. And you can see the hydroxy group, they are pentahydroxyhexanal because aldehyde group is there. 1, 2, 3, 4 and 5. Pentahydroxy, and if you see this stereocenter is R in nature, this stereocenter is S in nature, this fourth one carbon is R in nature and this one is R in nature. So we have designated D-glucose like this. Now how can we confirm the structure of D-glucose? How can we evaluate the structure of D-glucose? Simply we can say structure elucidation of D-glucose. As you know, glucose is the most important monosaccharide. It is far the most abundant monosaccharide which occur in nature. There are more glucose units in nature than any other organic molecule. Plus glucose is a typical of all monosaccharides. The chemistry of all other carbohydrate resolves around glucose molecule. We can study the structure of glucose in three parts. And this is open chain structure of D-glucose, second is configuration of D-glucose and cyclic structure of D-glucose. First of all, let us discuss more about the open chain structure of D-glucose. Glucose has the molecular formula C6H12O6. How can we decide the molecular formula? By elemental analysis, CHN analysis and molecular weight determination. Next point is this: glucose contain aldehyde group. How can we confirm that a particular molecule is having aldehyde group? Simply, you can see these are the number of reaction which shows that glucose contain a aldehyde group. First reaction is this: glucose molecule contains carbonyl group is shown by the formation of phenyl hydrazone and oxime. Second reaction, we will discuss in detail in coming slides the kind of reaction. Mild oxidation of glucose with bromine water gives a monocarboxylic acid, that is gluconic acid. Glucose is a reducing sugar and it is shown by the fact that it is reducing Tollens reagent Fehling solution. Both these tests are given by aldehydes only. These tests are not given by ketones. Hence, we can say that this glucose contain aldehyde group. Moreover, on reduction with sodium alcohol, glucose gives sorbitol and it is a hexahydric alcohol. Another reaction is there, oxidation with nitric acid. It is a strong oxidizing agent, you must know this. Dilute nitric acid oxidizes both the aldehyde group and this terminal CH2OH, that is alcoholic group of an aldose, to carboxylic group, that is COOH group. And when both the terminals get changes to, or we can say more precisely get oxidized to carboxylic group, it is known as generally for a aldose aldaric acid. For glucose we can say glucaric acid, for fructose we can say fluoric acid. So these dicarboxylic acid are known as aldaric acids. Oxidation of glucose with dilute nitric acid gives a dicarboxylic acid known as I told you, D-glucaric acid or saccharic acid. Another reaction is here, reaction with hydrogen iodide and phosphorus, reduction of glucose with hydriodic acid and red phosphorus gives N-hexane. What is N-hexane? When this is CH3, CH2, 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 CH2 and CH3, this will be N-hexane. The cyanohydrin obtained from glucose on hydrolysis followed by treatment of hydrogen iodide and phosphorus gives N-heptanoic acid. All the above facts suggest that glucose is a 6-carbon atom. As you know, both these facts what shows that it is a molecule of 6-carbon atom, straight chain pentahydroxyaldehyde, that is glucose is an aldohexose. And you can see the structure, we can write like this, open straight structure of glucose. And these are the reactions summarized over here, and if you can see, this is the structure of glucose, it containing one aldehyde group, and this is showing this kind of molecule. And here you can see this is phenylhydrazine. So the product is phenylhydrazone. With hydroxylamine, that is NH2OH, you will get oxime. You can see this is a oxime. With the Tollens reagent, it will gives a positive test. With the Fehling solution, again a positive test will be there. And with bromine water, you can see only terminal aldehyde group get oxidizes to carboxylic group. But while HNO3, that is dilute HNO3, both the terminal group get oxidizes to carboxylic acid, that is a dicarboxylic acid. Here you can see the reduction part, it will give you sorbitol, and here you can see with hydrogen iodide and phosphorus you will get N-hexane, that shows that there are 6 carbon atoms in a straight chain, and with acetic anhydride in presence of sodium acetate you are getting the product penta-O-acetyl glucose. So 5 hydroxyl groups are there. What this reaction shows? It shows with acetic anhydride and sodium acetate that the glucose molecule contains 5 hydroxy group that get changes with the help of acetic anhydride to penta-O-acetyl group. And with hydrogen cyanide followed by hydrolysis and with reaction hydrogen iodide and with heating you will get N-heptanoic acid, and this is your N-heptanoic acid. All these reactions shows that glucose is a straight chain molecule, and we can confirm the structure of glucose open chain structure. Now let us discuss the reaction of monosaccharide, that is glucose, especially with phenylhydrazine. You know what is hydrazine? NH2 NH2. When one H of hydrogen get replaced by phenyl, it will convert it to phenylhydrazine. And we are very much aware of the fact, we have discussed in detail in the series of aldehydes and ketone, that aldehydes and ketone when reacts with phenylhydrazine will yield the phenylhydrazone. The aldehydic group of an aldose reacts with carbonyl reagent as hydroxylamine and phenylhydrazine. With hydroxylamine, the product is expected oxime. With enough phenylhydrazine, we are talking about 3 molecules of phenylhydrazine. However, 3 molar equivalents of phenylhydrazine are consumed and a second phenylhydrazone group is introduced at carbon number 2. You can see over here, first molecule get introduced over here and second molecule get introduced over here, and this product is called a phenylosazone. Phenylosazone crystallize readily unlike sugars and are also useful derivatives for identifying sugars, that whether a particular solution or a compound contains sugar or is not, you can easily identify this reaction. Simply you have to react with the particular compound with phenylhydrazine. If there is a possibility of formation of osazone, definitely. So you can see this kind of reaction, it is a aldose, simply common name, and this is phenylosazone. What will be the mechanism for that particular reaction? The mechanism of osazone formation probably depends on a series of reaction. As you can see, this C double bond N, this functional group resembles very with this carbonyl group, that is carbon double bond oxygen. And here you can see how the mechanism took place. This is the base, it is abstracted the proton. First of all, you can see this aldehydic molecule get converted to osazone with the help of one molecule of phenylhydrazone with the nucleophilic addition reaction. You know what is nucleophilic addition reaction? It is given by aldehydes and ketone, I have discussed in detail. So this is the first molecule get converted to osazone. Now what happens after that? This base will abstract this proton, followed by this kind of rearrangement, will get this kind of tautomerization, and another 2 molecules can conserve over here, one here and one here, and you will get this kind of osazone. So clearly you can see what kind of rearrangement took place over here. When this base abstract proton from here, this is also get attacked by this proton and followed by tautomerization. Osazone formation results in a loss of stereocenter at carbon number 2, but does not affect other stereocenters. There are other stereocenters also, you can see over here, this carbon 3, 4, 5, these are the stereocenters still left. D-glucose and D-mannose, for example, yield the same phenylosazone. If you do a reaction with glucose and mannose, same reaction with phenylhydrazone, you will get the same kind of phenylosazone. So what we can say, it is explained by Emil Fischer, and he established the D-glucose, the structure of D-glucose and D-mannose having the same configuration about carbon number 3, 4 and 5. This is how he established the structure of D-glucose and D-mannose. You can see the structure of mannose around this carbon, these 2 carbon are exact same. So this kind of distereoisomers aldoses that differ in only one configuration, only one carbon atom are called epimers, and this process is called epimerization. And these are the D-glucose. So we can say what are the relation between D-glucose and D-mannose? These are epimers. Now we have discussed about the open chain structure. Now what is the configuration of D-glucose? here you can see what does it mean, configuration. If you see this glucose, every carbon atom has a particular position of hydrogen and hydroxyl group. If we are talking about a particular this structure, this is called configuration about these carbon atoms. So let us discuss it. Let us establish this conformation of D-glucose. The above structure of glucose shows that there are 4 chiral centers. If you can see this structure, 1, 2, 3, 4. There are 4 chiral centers. So how many stereoisomers possible? 4 you can see there are 24. There should be 24. And 16 stereoisomers, that is 8 pairs of enantiomers. All these 16 possible stereoisomers are now known. Some have been isolated from natural sources and others have been synthesized in the laboratory. The question now is, which structure represents the glucose out of these 16 stereoisomers? The problem was solved by Emil Fischer, a great scientist. He began his work on stereochemistry of D-glucose, or we can say plus glucose. He gave the configuration of glucose and was also able to synthesize and summarize all the other isomers. And for this great work, he was awarded with the Nobel Prize in 1902. If you can see, this is a great picture. If you can see so many isomers, how these form. I will discuss in detail what is Kolani synthesis. What is this? It is a process we can increase one stereocenter of a molecule simply by Kolani synthesis. If you can see, this is D plus glyceraldehyde. It contains only one chiral center. This one is one chiral center. If we do, you can see lengthen chain. If we increase this chain by Kolani synthesis, we are having 2 kind of isomers, stereoisomers. This is D-erythrose and this is D-threose. When the hydroxyl group are on the same side, it will be your D-erythrose, and when these are on opposite side, it will be your threose. Now by again doing Kolani synthesis with this D-erythrose, again 2 possibilities are there. One is like that, another one is like that. So this is your D-ribose and this is D-arabinose. From this D-threose we will get same by Kolani synthesis. If we upgraded this chain, you can see this arrow, these reactions are reversible also. You can degrade also the series, but first of all we have to look the upgradation of the series. When we upgrade this series by Kolani synthesis, it will give you 2 kind of enantiomers. This is gylose and this is D-lysose. From this D-ribose we will get D-allose. If you see this is stereocenter and see the difference, this is D-altrose. And from D-arabinose, here you can see D-glucose and D-mannose. From D-gylose you have D-gulose and D-iodose. From D-lysose you have D-galactose and D-tellose. These we can read from the chart, but how can we establish that out of these stereoisomers, from upgrading this glyceraldehyde, which one is glucose? That this program, if we see, we have done point out the number also. This is D-allose is number 1, D-altrose is number 2, D-glucose is number 3, D-mannose is 4, D-gulose is 5, D-iodose is 6, D-galactose is 7 and D-tellose is 8. Out of these possible stereoisomer, which is the glucose one? It is established by Emil Fischer. How? Since an aldose has 4 stereocenters, stereomers are possible, one of which is glucose. Fischer arbitrarily decided to limit his extension only to 8 with the D configuration given in figure. First of all, he took only 8 structures arbitrarily. It was not decided as written. Fischer realized that he would be able to differentiate between enantiomeric configurations because methods of determining the absolute configuration of organic compound had not been developed. It was not until 1951 and Burgett determined the absolute configuration of L-tartaric acid and hence D-glyceraldehyde that Fischer's arbitrary assignment of D-glucose to the family we call the D family was known to be correct. Fischer assignment of structure 3 glucose was based on the following reasoning. He has given that the structure number 3 is glucose. How he come to concluded that this is the structure only D-glucose? First of all, what he did, the nitric acid oxidation of glucose gives an optically active aldaric acid. You know what are the optically active compounds? If a compound is having stereocenter, it will be optically active. That a molecule must contain a asymmetric chiral atom. So, nitric acid oxidation of glucose gives an optically active. Hence, this reaction will eliminate structure number 1 and 7. If you see structure number 1 and structure number 7, if we do oxidation of these two compounds with nitric acid, if you remember, both the terminal group get oxidized to carboxylic acid. This 7 also. So, both are the same, both will contain a meso compound. If these two terminals get oxidized to carboxylic acid, then this molecule will be a meso compound. So, it will not at all a optically active compound. Same here with 1 also. So, these two structures discarded the structure of glucose. Degradation of D-glucose gives arabinose. You know what is degradation? Degradation of a monosaccharide by one stereocenter. So, we will continue this configuration of D-glucose. How can we establish whether out of these 8 stereoisomers which structure is glucose? We will discuss in detail thereafter. Thank you so much. Hope you understood all these reactions, chemical reaction, which shows that what could be the open chain structure of glucose. Thank you so much.
Thank you, Dr. Vandana. Friends, thank you for joining for this part of the series. We'll continue after a short break onto the same topic of carbohydrates, part 1, under the topic of natural products and spectroscopy. Meet you after a short break. Welcome back, friends, to the session of live lectures. Before this break, we were discussing about carbohydrates under the topic of natural product and spectroscopy. Let's move on to the other half of the lecture, and let's welcome Dr. Vandana once again.
Thank you so much.
Vandana, welcome once again, and let's start on to the topic.
Hello viewers, we were discussing about carbohydrates. In carbohydrates, we were discussing about the structure of glucose. We have discussed in previous part the open chain structure, and you know how we come to conclude that this should be the open chain structure of glucose. Now we are discussing a very important part, this configuration, for which Emil Fischer was awarded by the Nobel Prize. So let us continue this. We have discussed that these are the possible stereoisomers by the upgradation of glyceraldehyde. These are the possible structure for the glucose. How can we discard it, or how can we choose that this structure can only be glucose? I have already stated that Emil Fischer arbitrarily chooses these 8 stereoisomers only. And we have discarded the possibility of 1 and 7. How? Because when we did oxidation with this, we will get optically active, and these 2 compounds will not give optically active. This will give meso compounds, so the possibility of 1 and 7 can be discarded. Degradation of D-glucose gives arabinose. So, if we do degradation, we get arabinose, and nitric acid oxidation of arabinose gives an optically active aldaric acid. So, there are 2 reactions we are talking about at the same time. First of all, you need to do the degradation of glucose, it gives a arabinose, and nitric acid oxidation of arabinose gives optically active compound. So, this means that arabinose cannot have configuration 9 or 11. If you see the structure of 9 and structure of 11, if we did oxidation, if we do oxidation of these 2 compounds, that is, this is structure and this is structure, with nitric acid, it is a strong oxidizing agent, and both the terminals get oxidized to carboxylic acid. So, again it will be a optically inactive compound. Same here, if you see, this will be a meso compound. If we do oxidation, these 2 terminal get changes to carboxylic acid, and because it will contains a plane of symmetry, it is a meso compound. You know what is meso compound? When a molecule contains a plane of symmetry, that is, the molecule is symmetric from the plane of symmetry, any plane of symmetry. If we see, this will be becomes on oxidation COH, COH, and if we see from this plane, it will be a meso compound. So, these are not the possibilities for the glucose. So, 5, 6 and 2 are also discarded. These structures, that is, when we thought about the upgradation of this structure, these are not the possibility. 2, 5, 6 are discarded for the possibility of a structure of D-glucose. And this leaves what? Only structure 3, 4 and 8 for the possibilities of glucose. If you see here, only 3, 4 and 8 will left for this structure of glucose. We have discarded all these possibilities. A Kolani Fischer synthesis beginning with arabinose gives glucose and mannose. This we knows that when we are doing upgradation of arabinose, we will get glucose and mannose. And nitric acid oxidation of mannose gives an optically active aldaric acid. This together with the fact glucose yields a different but also optically active aldaric acid establishes that structure 10 as the structure of arabinose. So, here we are going back. First of all, we are establishing the structure of arabinose, and because we know that upgradation of arabinose will give glucose and mannose, so we have to find out which is the structure of arabinose. And if you see this together with the fact glucose yields a different but optically active aldaric acid, and if arabinose has been represented by structure 12, a Kolani Fischer synthesis would have been giving the 2 aldohexoses 7 and 8, and one of which 7 would end optically inactive. So, this is not possible. Now, it is discarded the possibility of this 8 is also not possible, because this is not possible. So, we will get only 3 possibility now, 3 and 4. 2 structure now remain, 3 and 4. One structure represents plus glucose and one represents plus mannose. Fischer realized that plus glucose and plus mannose were epimeric at carbon number 2. We know if the configuration is changed at carbon number 2, these are epimers. We have discussed it in earlier slide, but a decision as to which compound was represented by which structure was the most difficult task for him. What he did, Fischer had already developed a method for effectively interchanging the two groups. If you know about stereochemistry, 180 rotation is allowed rotation. The configuration of a molecule will not change at all if we rotate the group by 180 degree. And these are the end groups CHO, that is aldehyde group, and alcoholic group of the aldose chain. And with brilliant logic, Fischer realized that if plus glucose had structure 4, an interchange of end groups would yield the same aldohexose. So the problem can be viewed by considering overall effect on glucose or mannose of a sequence of reactions with interchange the two groups. We will interchange the end groups in both the structure. First of all, if plus mannose has a structure 4, an interchange of end group will yield the same aldohexose. On the other hand, if plus glucose has a structure 3, an end group interchange will yield a different aldohexose, and which is L sugar, because we knows it that if we interchange this plus glucose, then we will get a different aldohexose, and this is done by only structure 3, and which is a L sugar. It is an enantiomer of D-Glucose. You can see here, if we interchanging these two groups, we will get this kind of a structure, and which is equivalent to this. Why it is equivalent to this? Because we interchanging these terminal groups by 180 rotation. And here is the structure number 3. It is giving different, you can see different sugar is here, and what is that? Nothing but the enantiomer of L-Glucose, and this is D-Glucose, this is L-Glucose. This new aldohexose, if it were formed, would be an L sugar, and it will be the mirror reflection of D-Glucose. Thus its name would be L-Glucose. Fischer carried out the end group interchange starting with plus glucose, and the product was the new aldohexose. This come out proved that glucose has structure number 3 only, because it gives a different. It also established automatically the structure number 4 for mannose, and it also proves the structure of L-Glucose. Here he proves 3 structure: D-Glucose, D-mannose, and L-Glucose. The procedure Fischer used for interchanging the ends of the glucose chain began with one of the gamma lactones of D-glucaric acid and was carried out. Notice in this synthesis that second reduction with sodium amalgam is carried out at pH 3 to 5. Under these conditions, reduction of the lactone yields an aldehyde and not a primary alcohol. Here you can see, this is gamma lactone of D-glucaric acid. First of all, you will get this kind of D-gluconic acid with reduction, and this is the another isomer, that is gamma aldolactone, and with 3 to 5 pH you will get this kind of a structure. This is L-Glucose, and this is the structure we have proved in the configuration of D-glucose. So viewers, you have seen, first of all we have discussed about the open chain structure of glucose by considering all simple reactions that we have concluded from the animal analysis what should be the molecular formula of glucose. If it is containing aldehyde group, because of several reaction prove that it is containing aldehyde group. When we are doing reaction with acetic anhydride, it shows the 5-hydroxyl group, and N-hexane proves that it contains 6 carbon atom in a single chain. Then we have discussed about the configuration, what should be the configuration of D-glucose. Now coming to the next, cyclic structure of D-glucose. The above structure which we have discussed till now could not account completely for its chemical behavior. How? How can we concluded that there is another possibility structure for glucose, that is cyclic structure. D-glucose fails to undergo certain reactions typical of aldehydes. We are saying that glucose is containing aldehyde group, so it must give reaction given by the aldehyde group, but it does not. For example, it does not form a bisulfite addition product and gives a negative test with Schiff's reagent, although it is a readily oxidized. The pentacetate formed by the acetic anhydride with glucose and the pentamethyl ether derivatives of glucose are not oxidized by either by Tollens reagent or Fehling solution, and also do not form phenyl hydrazone or bisulfide addition product. One of the ether groupings in pentamethyl derivatives is highly reactive, others are not. It undergoes hydrolysis in dilute acids to a tetramethyl derivatives. All these reactions are unexpected from the structure we have studied till now. The tetramethyl derivative reduces tolerance reagent as effectively as glucose itself. So, glucose, what we came to know, D-glucose exists in two isomeric forms which undergo mutarotation. What is that? We will discuss in detail. When crystals of ordinary glucose, how it comes in notice, when crystals of ordinary glucose melting point 146 degrees Celsius was dissolved in water, its specific rotation comes out plus 112 degree, and on keeping this solution the value drops from 112 to 52.5. How? When glucose is obtained from the fresh hot concentrated solution, its specific rotation changes from an initial value of plus 19 to an equilibrium value of 52.5, and the change in rotation of these two equilibrium value is called mutarotation. So, here is a process which happens actually with glucose that is responsible for these different kind of reaction. As you can see, these two different isomers here, we are saying that one is alpha isomer, another is beta. We will discuss in detail in coming slide. You can see alpha is having this specific rotation, that is plus 112, and beta is having plus 19, and these isomers are interchangeable via this 52.5 degree specific rotation. Plus D-glucose forms two isomeric methyl D-glucoside, methyl alpha D-glucoside and methyl beta D-glucoside, under condition which normally convert enaldehyde to hemiacetal or acetal derivative. Here you can see this kind of reaction is possible. We know aldehydes reacts with alcohol in presence of anhydrous HCl to form hemiacetal or acetal. Here you can see what should be the structure of hemiacetal and acetal. Here you can see when one group is replaced, one group is introduced, this is hemiacetal, two acetyl group is there, this is acetal. These glucosides do not reduce tolerance reagent and failing solution and do not undergo mutarotation at all. That means they are comparatively quite stable under mild acidic or mild basic conditions. Furthermore, they have different melting point, as we have observed in the case we have seen in earlier slide that alpha is having something different melting point while beta is having something different. With the specific rotation is also different for both the isomers. The isomer of higher positive rotation is called methyl alpha D-glucoside and other methyl beta D-glucoside that has melting point 107. The above observation cannot be explained on the basis of open chain structure of glucose. Certainly, it is obviously that aldehyde group in the glucose molecule is not free at all. You must remember, viewers, that what is actually come in our mind, that aldehyde group in glucose is not free. It is tied up with one of the hydroxyl groups which is turned to be at carbon number 5 to form a hemiacetal structure. So, there is no possibility all the time open chain structure of the glucose. Sometimes open chain structure is there, sometimes other isomers are there. The cyclic forms of D-glucose are hemiacetals actually, formed by an intramolecular reaction of hydroxyl group at carbon number 5 with the aldehyde group, the top one. Thus, we get a cyclic structure for the glucose molecule. How it forms, we will discuss in coming slide, how the open chain structure get converted to cyclic structure in solution. What happens through this mutarotation, actually, the new chiral center is created at carbon number 1 by the hemiacetal formation, and there are therefore two more stereoisomeric forms of the D-glucose. And we can designate these two as alpha D-glucose. What are these? We will discuss in detail what are the structure for alpha and for beta D-glucose. These are distereoisomers differing in configuration at carbon number 1, and such a pair of distereomers are called anomers. Here you can see a great picture. First of all, you can see this is the open chain structure of glucose. We have certainly establish this structure. Now what happens? Actually, if you can see that at the last, this is the open chain structure, something happens over here and we will get two kind of isomers. This is alpha D glucopyranose, because it will resemble with pyranose, and this is beta D glucopyranose. And if you see carefully this structure, or we can say the configuration around each carbon atom, every carbon atom is same except this one. If you can see this hydroxyl group and this hydroxyl group, one is axial, another one is equatorial. How it happens? Let us see more carefully. This is the glucose structure. We have a nomenclature, each carbon number. This is the plane projection formula. When a model of this is made, it will coiled as follows. We can coil this molecule like this. Here you can see we were designating the carbon number, and here you can see 1, 2, 3, 4, 5, 6. This is nothing but a coiled form of this open chain structure of glucose. Now what happens over here? If you can see these arrows carefully, if the group attached to carbon number 4 is pivoted, means rotated on its own axis, as the arrows indicate, we have the and followed by, first of all you have to pivot this and then rotating this. This will group coming to this will coming to this, and this will coming to this. So what are the structure made from here? You can see this is the possibility. This will be the open chain form of glucose. Here you can see. Now what happens? This OH group adds to this carbonyl group, because you know this carbonyl group is aldehyde group, and aldehyde group is giving nucleophilic addition reaction. So certainly this OH group adds to this carbonyl group to close a ring of 6 atoms and make a cyclic hemiacetal. Here you can see how it took place. This double bond, or we can say pi electrons, these pi electrons get attracted by the more electronegative atom. This is oxygen atom, so it will become electrophilic in nature, and this oxygen being containing a lone pair of electron is behaves as a nucleophile, a source of nucleophile, and this kind of cyclic structure. These are the two possibilities as we talking about the stereoisomers, and you can see in one place it will be to ring left, or in this will be left to this ring, this will be right, and these two stereoisomers are known as, if this hydroxyl groups lies on below, or we can say on right, we can draw this structure in a straight way also. So this is alpha D glucopyranose, because it resembles with pyranose structure. Pyran, it is it is a sugar, so O's is there, it is resembled with pyran, so we can say glucopyranose, and because of this hydroxyl group, because of the position of this hydroxyl group, this is alpha, and because of the hydroxyl group at the last asymmetric carbon atom, it is D. So these are two possibilities, alpha D glucopyranose and beta D glucopyranose. Let us see once again what happens over here. This is the cyclic structure, how this is also called the mutarotation. The formation of hemiacetal of glucose, or we can say cyclic structure of glucose from the open chain structure. So probably we can explain what was happen in case of when we see the solution of glucose. And you can see this way also, this is alpha D glucose and this is beta D glucose. When you see this structure, Fischer projection, here you can see this hydroxyl group lies on the right hand side and this hydroxyl group lies on the left hand side. X-ray analysis of D-glucose indicates that in alpha anomer, the hydroxyl group at C1 and C2 are cis to one another and trans in beta anomer. The above representation are according to Fischer projections. Hydroxyl group on the same side in the Fischer projection of hemiacetal are cis to each other, and those on the opposite sides are trans. We can represent this type also. The C1 hydroxyl group is on the right in the Fischer projection of alpha D glucose and on the left beta D glucose. We can represent like this also by this curved arrow, right? We can represent like this, we can represent like in this chair form also. This the Haworth, these are called Haworth structure, because this mechanism is given by this the formation of cyclic structure from the open chain structure of glucose is given by Haworth. So, these alpha and beta isomers of D-glucose are called Haworth structure. As they are derived from the parent heterocyclic parent, we have discussed it. In these projections, the CH2OH is written as up for the D sugars and L for the, if you can see, for the D sugars, and D sugars on the OH at C1 will be down in the alpha, and for beta it will be up. We have discussed. Here are the more structure you can see. These are the possible. This is the Fischer projection formula. This is, we can represent this structure equivalently to this kind of structure. This is called circle and line formula. You can see each carbon atom, the stereocenter carbon, which is stereo symmetric in nature, which is chiral in nature, is represented by this black dot. So, there are circles 1, 2, 3, 4. These carbon atoms are not chiral, they are symmetric in nature. So, these are not represented by circle. Here also you can see the plain lines and the wedge lines are also here. So, it is called wedge line, heavy lines are there, wedge line, dashed wedge formula. And these are, you can see, these are the Haworth formulas, alpha, beta, and these are equivalent to these structure. This is alpha D. So, any representation you can represent for a glucose. This is the open chain formula. These are the Haworth structure, alpha and beta, and these are the chair form of alpha and beta D-glucopyranose. So, how can we define what is mutarotation? What we need to write when we are talking about mutarotation? Simply, cyclic hemiacetal structure for D-glucose comes from experiment in which both alpha and beta forms have been isolated. Ordinary D-glucose has a melting point of 146 degree, that you must notice. However, when D-glucose is crystallized by evaporating in aqueous solution kept above 98 degrees Celsius, a second form of D-glucose with a melting point with a different melting point can be obtained, that is your beta. When the optical isomers rotations of these two forms are measured, they are found to be significantly different. But when an aqueous solution of either form is allowed to stand, its rotation changes. It will not at all the same value. The specific rotation of one form decreases, the rotation of either other increases until both solutions show the same value. A solution of ordinary D-glucose, which is having the melting point 146, has an initial specific rotation of 112 plus, but ultimately the specific rotation of this solution falls to plus 52.7 degree. A solution of second form of D-glucose melting point with melting point 150 degrees Celsius has an initial specific rotation of approximately 90 degree, or we can say precisely plus 18.7 degree, but slowly the specific rotation of this solution rises to 52.7. If you notice, both the specific rotation comes out to be or at a value of 52.7, and this situation is called equilibrium. This changes in rotation toward an equilibrium value is called nothing but mutarotation. The explanation of this mutarotation lies in the existence of equilibrium, the open chain form of D-glucose and the alpha beta forms of cyclic hemiacetals. And you can see, if you have to define what is mutarotation, you necessarily draw these structure. These are the hemiacetal structure of glucose. It is alpha D glucopyranose. You must show the melting point as well as the specific rotation. You can see this is the perfect representation of mutarotation in glucose. Here you can see this is the open chain structure of D-glucose, and it is interchangeable to alpha as well as to beta. Alpha is having different melting point with different specific rotation with respect to beta. So, this interchangeable is called interchanges from one form to another form, and at equilibrium it will be a open chain structure of glucose. So, you can see this is the mutarotation. X-ray analysis has confirmed that ordinary D-glucose has the alpha configuration at the anomeric carbon atom, and that higher melting point has the beta configuration. The concentration of open chain D-glucose in a solution at equilibrium is very small. solution of D-glucose give no observable UV or IR observation band for a carbonyl group, and solution of D-glucose gives a negative test with Schiff base reagent, a special reagent that require a relatively high concentration of free aldehyde group rather than a hemiacetal in order to give a positive test. So, viewers, you have understood, we have started with the carbohydrates. We have discussed in detail about the open chain structure of glucose. We have discussed in detail how can we assign a particular configuration out of 8 structure to a particular glucose, that is D-glucose, and we have discussed in detail what how a cyclic structure is formed through mutarotation in a solution. Hope you understood this. Thank you so much.
Thank you, Dr. Vandana. And we thank you all for watching this series of live lectures. If you have any questions regarding this lecture or you have any suggestions regarding the lecture, you may write it to us at our mail ID, which is info.cec@nic.in. We once again thank Dr. Vandana for a very fabulous lecture, and we thank you for joining with us for this lecture.